So now we want to talk about how we can use L'Hopital's rule to compute different limits when you have an indeterminate form that's not necessarily of the type 0 over 0 or infinity over infinity. Okay, there's lots of other different types of indeterminate forms. So let's say you have a function of the form, I don't know, or you're taking the limit as x goes to a particular value of f of x times g of x, right? And the first function f of x is heading towards 0 and the second function g of x is heading towards some infinity. That would give you an indeterminate form. That limit may or may not exist. Similarly, if you had the limit as x goes to a of some function f of x minus g of x, and both f of x and g of x were heading towards infinity, then this is an indeterminate form. This limit may or may not exist depending on how quickly each one is going to infinity. And then in this last case, we have different powers here. So if we were taking the limit as x goes to a of some function f of x raised to another function g of x, and f and g were both heading towards 0, or if f was heading towards an infinity and g was heading towards 0, or if f was heading towards 1 and g was heading towards some infinity, these would all be indeterminate forms. Those limits may or may not exist, and we need to do some other extra work to try to figure out what those limits should be. Now, there's other different types of functions that are not indeterminate forms, that are, I guess you could call them determinate forms. If you're finding the product of two functions, or the limit of a product of two functions, and both of them are infinity, both positive or both negative, or even one of each, then this limit will exist. Well, it'll exist in that it will be either positive or negative infinity. Okay, so we have to really be careful with how we say that. Technically, an infinite limit doesn't exist, but we will know that the limit will be either positive or negative infinity. It is determinate in that way. In the second case, if you have 0 over infinity or some other whole number, or not necessarily whole number, some other real number over an infinity, where you have f over g of x, then this limit does exist and it's equal to 0. Right, we had talked about this when we did, 1 over x, for instance. And in this last case, if your numerator is heading towards an infinity and your denominator is heading towards 0, then this limit is going to also be positive or negative infinity. So these are determinate forms. They don't require any sort of L'Hopital's rule or any sort of work. You just have to think about whether it should be positive or negative infinity for these two cases. And in this case, in the middle, it would have to be 0. All right, so the problem is L'Hopital's rule only works when you're looking at f of x over g of x, right? And you get an indeterminate form of the type 0 over 0 or infinity over infinity. These are different types of indeterminate forms, but we can use some sort of algebra sometimes to try and rewrite this in an indeterminate form where L'Hopital's rule applies. So let me show you what I mean. If we're doing this function here, we're taking the limit as x goes to 0 from the right of x squared times ln of x. Well, okay, this is an indeterminate form, I claim, of the type 0 times, positive or negative infinity, right? Because as x goes to 0, certainly x squared is going to go to 0, and as x goes to 0 from the right, remember ln of x looks like this. As x approaches 0 from the right, this function's heading down towards negative infinity. Okay, so this is an indeterminate form. This limit may or may not exist, we're not sure yet. But we can't use L'Hopital's rule, at least not right away, because L'Hopital's rule only applies to indeterminate forms of the type 0 over 0 or some infinity over another infinity. So we want to rewrite this function in such a way that L'Hopital's rule does apply. Okay, how do we do that? Well, if you have a product of two functions, the natural way to do this is to rewrite it as some sort of a quotient, right? Some function over another function. Now you could either try to bring this x squared into the denominator, or you can bring the ln of x into the denominator. But this is going to be a harder one to move to the denominator because then we'll have ln of x to the -1 power, which would require a chain rule to take the derivative, which is kind of a mess. So here's what I'm going to do. I'm going to rewrite this as 0 to the right. Ln of x is going to stay on top, but we're going to move this x squared term down into a denominator. Right, we'll move it down here and change the exponent to x to the -2. Now this is an indeterminate form of the type infinity over infinity. Technically it'd be negative infinity here over positive infinity, but either way, right? If you have infinite on top and infinite on the bottom, it doesn't matter the sign, L'Hopital's rule is still going to apply. So because L'Hopital's rule applies, we know that this limit is going to be equal to the limit as x goes to 0 from the right. This is by L'Hopital's rule. Oops. Of the derivative of the top over the derivative of the bottom. All right, the derivative of ln of x is 1 over x, and the derivative of x to the negative 2 would be negative 2x to the negative 3. Okay, so this is equal to, well, what is this limit going to be? If we just try to plug in 0 here, we're going to end up with 1 over 0, which is an infinite on top, and this limit would also be an infinite limit. So maybe instead of just using direct substitution, before I do that, I should try to use some algebra here, right? Remember that I can rewrite, so this limit as x goes to 0 from the right. I can rewrite the top as x to the negative 1, and because I have a power of x on top and a power of x on the bottom, using our exponent rules, I can subtract those exponents. So let me just pull out this negative 2 as a factor of 1/2, negative 1/2 I mean. And according to my exponent rules, if I have a negative 1 on top and a negative 3 on the bottom, I can subtract them. So this is x to the power of negative 1 minus negative 3. So this is negative 1/2 times x to the power of, I can add a positive 3, and it's just x squared. So by simplifying this function just using algebra, now I can see that it's in a form where this limit does exist, right? Of course, this limit exists as x goes to 0. I can plug in x equals 0 using direct substitution and just get negative 1/2 times 0 squared, which is just plain 0. Okay. Right? So we started with an indeterminate form of the type 0 times infinity, and we were able to rewrite it by moving one of those functions into the denominator and then applying L'Hopital's rule. Okay. Let's try a similar example, but this time with a different indeterminate form. Let's look at the function cotangent of x minus cosecant of x, and we'll look at the limit as x goes to 0 from the right. Okay. First, we want to try direct substitution and see if that works. It doesn't work, but why? What is cotangent of 0? What is cosecant of 0? If you don't remember right off the bat, then it might be helpful to rewrite these using the definitions of these functions. Remember that cotangent is just the reciprocal of the tangent function. So tangent sine over cosine, therefore cotangent would be cosine over sine. Okay, this hopefully we know how to do. We know how to evaluate cosine of 0 and sine of 0. Similarly, cosecant is the inverse of the sine function, so, or I should say the reciprocal of the sine function. So it's 1 over sine of x. All right, now if I were to try to use direct substitution here, in the first case I'd get cosine of 0 over sine of 0 minus 1 over sine of 0. Cosine of 0 is 1, sine of 0 is 0, so we get 1 over 0 minus 1 over 0, and 1 over 0 itself is an indeterminate form, or it's a determinate form that's heading towards an infinity. So this is going to be an infinite over minus an infinite indeterminate form, infinity minus infinity. Right? This is an indeterminate form, therefore this original limit may or may not exist, but we're not sure yet. So what we want to be able to do is to rewrite this in some form so that L'Hopital's rule would apply, and then use L'Hopital's rule. And there's a natural way to do that based on how I've written it right here. Right? L'Hopital's rule applies when you have some function divided by another function and it's giving you an indeterminate form of the type 0 over 0 or infinity over infinity. So let's try to rewrite this difference of two functions as a single quotient. Right? So I'm going to just combine these two fractions into one fraction. and I get the limit as x goes to 0 from the right of, I already have common denominators, this couldn't be any easier, well maybe, sine of x is our denominator, and our numerator is cosine of x minus 1. All right, now this is an indeterminate form of the type 0 over 0, because if I plugged in x equals 0, I'd get 1 minus 1 over 0. Right, cosine of 0 is 1, sine of 0 is 0, which means L'Hopital's rule now applies. Okay, so by L'Hopital's rule, we can take the derivative of the top and the bottom, and the limits will be equal. This is equal to the limit as x goes to 0 from the right of the derivative of cosine, which is, remember, the derivative of cosine is negative sine of x. The derivative of negative 1 is nothing, and the derivative of the denominator sine would be cosine of x. Okay, now we try direct substitution again. Plug in x equals 0, what do we get? We would get negative sine of 0 over cosine of 0. Negative sine of 0 is just 0, and cosine of 0 is 1. 0 over 1 is a real number, it's equal to 0. So this limit does exist, and it's equal to 0. Okay. Now we had a whole bunch of other different types of indeterminate forms that we talked about, right? All of these different indeterminate forms, and we've gone over how to rewrite the first two in a form that we can apply L'Hopital's rule. There's similar methods for these last three. In the interest of time and all of the missed time that we've had so far, I'm going to skip the last three, but you'll see a lot more of them when you get to Calculus 2. So these are the types that you want to be looking out for in this class.